Okay. So I'll introduce the paper with, named Quantum Finite Automata, a modern introduction today. So maybe lots of members know about the finite automata. So this presentation will be briefly proceed. Yeah. So I will introduce a classical finite automata and quantum finite automata, I believe. Yeah. So in Google, we can, if we type automata, then some, so some hand derived, yeah, models. Yeah. But in computer science and mathematics, in dictionary there are two definitions, and the first one is in the figure before, and our automata is defined as the second definition, a machine that performs a function according to a predetermined set of coded instructions and capable of a range of programmed responses to different circumstances. So a lot of classical automata theory was developed in 1950s and 80s. So the automata is used in regular expressions in programming languages and lexical analysis, such as parsing in compilers. And our computer, Turing machine, is also automata, and formal language is strongly related with this automata theory. And maybe everyone heard about the Conway's Life game. Yeah, and this is a cellular automata example. And so automata is widely used in computer science and linguistics and mathematics. So basically, our automaton gets an input stream. This is not it. On input string, get an input string such as instance, and it automaton interpreted with predetermined rules. There are some rules and internal memory, and it will change the automaton state and given strings, and finally the word, the input string will be recognized or not. We call accepted. The word is accepted if it is recognized, and it is rejected if it is not recognized. So this is a vending machine model, which accepts $6. And if we put $1 coin, $1, then 6, 5, 4, 3, 2, 1, and 0. This is the final state and initial state. Yeah. And we, if the automaton gets $5 and $1, then it will 6 to 1 to 0 state. This is an example of automaton, and this is non-deterministic, since whether it is deterministic automaton, since if we put $1, then it must go to $5, not 4 or 3 or itself. Yeah. So this is an example of deterministic finite automaton. And the classical automata are classified with their memory types. Before this example has no memory, but and that is final state machine. And there are some automaton with stack memory that is called push down automata, and bounded linear tape if the automaton has a bounded linear tape, then it is called linear bounded automata, and unbounded linear tape will make it Turing machine. This is the basic automata. So there are some stochastically that which executes stochastically. Sorry, stochastically, and this is named with probabilistic finite automata. Actually, quantum finite automata is related to PFA, but I will introduce the basic model FSM and QFA only. Since PFA definition is very similar to QFA, so I don't need to introduce that now. And basic quantum automata, there are some quantum automata. Basically 3 examples. Quantum finite automaton. This is correspond to the finite state machine, and quantum cellular automaton. This is a special case of quantum Turing machine. Okay, so we will only see about the QFA. And to define a classical finite automata, we need some mathematical definitions. Mathematics. I avoided 2 rigorous things, but it is necessary to explain. So our alphabet is denoted as sigma, capital sigma, and this is a set of letters such as 0 and 1 or A to Z. And we will denote sigma star as a set of strings generated with sigma, and epsilon denotes length 0 string. So sigma 1 star becomes epsilon 0 1 0 0 0 1 1 0 1 1, and so on. So we also define sigma plus, which excludes only epsilon of sigma star. Okay, and we'll define a language. Language is a subset of sigma star. This is called formal language, and that's CS parts topic. So, yeah, some research topic. And we define finite state machine, which in 2 cases. One is deterministic finite automaton, and that is non-deterministic finite automaton. Each are DFA and NFA, and this is an example of NFA, and this is an example of DFA. So it gets A, then we don't know where it goes. Maybe the input to maybe it still remains its place or go to right state. But in this model, we can always determine where the state evolves. So, and 2 automata are equivalent. Yeah. The equivalence means here is both automaton can recognize same words said, the same language. Example, AAB can be recognized this with AAB, and in here AAB, and this cannot recognize BAA. Sorry, this cannot recognize ABA, since ABA where to go we don't know, and in here ABA, and this mode in here we didn't we cannot reach the final state. So this is the classical automaton model. And the mathematical definition is DFA is defined as a principal A with Q sigma delta Q0 F. That is Q is a set of states and sigma is an alphabet and delta is a transition function. And Q0 is initial state and F is a set of acceptable states. In before picture, there was only one final state, but there can be many final states, and initial state can also be a final state. So, and delta, I need to explain the delta. This is in DFA, delta is a function. So NFA, we cannot define it as a function in the form, since in here we cannot define the A and the execution when it gets A. But in here, every state can accept any alphabet. So we denote it as a transition function delta. So this is real definition of DFA, and surprisingly, any NFA is equivalent with some complete DFA. I used complete to make it a whole function, not a partial function. And this, if you are wondering the proof of the equivalence between NFA and complete DFA, then personally ask me, then I will give you some additional materials. And so we will forget NFA. We only use complete DFA. And DFA works this process, but just think the graph. This is just a rigorous definition to forget the graph, but it is equivalent with a well-defined graph. So just imagine this picture. This is a good example of complete DFA. And delta star, we denote delta star to when we get a word, then so previously I said that an automaton gets an input string, and delta star is shows the process of the input string to final state directly. Just think easily. There are language that is called regular language. This is a subset of sigma star, and which is accepted with DFA. They are all a language that is accepted with a DFA that is called regular. And this is an example of non-regular language, since DFA cannot remember how many A appeared. Yeah, it has no memory. So it can be recognized with the higher automaton, such as push-down automata or Turing machine, they can accept this language, but finite automaton can finite states machine cannot accept this language, and we will see that QFA will be I will recognize some non-regular languages to show QFA is more powerful than GFA. Okay, and in quantum case, we need to change the state to quantum state and the transition function to some operators to change the quantum state. And the instructions will be used as a string. It remains same, and but each letter will be substitute to some unitary operator. Okay, so I will define the QFA as this. So in the basis, Q1 to Qn, Dn is an automorph basis of Hilbert space Hn, and the real-time quantum finite automaton is defined as a quintuple, the same form, such as with Q is a set of states and sigma is an alphabet, and U sigma is a unitary matrix, which is correspond to a letter sigma in capital sigma in the alphabet, and Q1 is an initial state, and QA is a set of accepting states. Yeah. So the state evolution will be similar. Will be operate similar with the GFA, but it changes some unitary operator. Yeah. It is called real-time QFA since it does not save the string, but as time goes, it take a letter and evolve, and take letter, evolve, take letter, evolve. So I will still say QFA after, but in this material, text will be ArchQFA. Yeah. And we need to slightly change the language, since it accepts a state with some probability that cannot be one. So there are cut points. So n least lambda. The FM is defined as the probability that the last state is accepted. Yeah. So the probability is greater than lambda, then it is accepted, and less than or equal to lambda, then it rejected in our language with cut point. So there are terminology that quantum non-determinism, that is the case of lambda is equal to 0. If there are some, if the probabilities, it excludes only the 0 probability case. That is called quantum non-determinism. And we'll introduce 2 examples that can see that QFA is more powerful than GFA. So suppose that this language is non-regular language. I will not prove this, but it is known fact. And I will say any q, that the set of the word that is generated with A and B, and the word contains different number of A and B. I will call this language NQ. And if we define QFA with two operators, U plus minus square root 2 pi, then the state will only so there are two states, Q1 and Q2, and if the machine get A, then it becomes it rotates square root 2 pi, and B, then it rotates clockwise. But since square root 2 is not a rational number, so the number of A and B is different, and the states will never remain in the Q1 axis, plus Q1 or minus Q1. There can be the final state, if the A and B number is different. So if we think the language L0M, then it is equal to the NEQ. So we see that QFE is, I can recognize non-regular language. And another example, this is a promise problem. And the promise problem is as P, yes, consists with PS and P node set, and the automaton must accept if the element of P, yes set, is injected, and must reject if the P no element is the input string. But otherwise, if the word is contains nor PS or nor P no, then the probability is out of our interest. Yeah. So in generally, QFA cannot be more succinct than the real-time DFA for the exact language recognition, but some cases it is it is more succinct than RTDFA, such as this. If the set is given as the right parenthesis and if you define the problem as the first yes set becomes the alphabet is given as only with a one element set, and one element alphabet. If we accept A is the A to the J times 2 to the K, then we will always accept this language. And if the J becomes odd integer, then will always reject the set. Then we define theta as pi over 2 to the k plus 1, and the QFA contains an operator, theta, rotation operator, theta. Then it can solve even odd k with only with two states, since if we get 2 to the k number of A, then the initial state becomes Q2. Then if we measure the probability that it is in Q1, then it must be 0. And all the times of 2 to the k, then it always becomes plus Q2 or minus Q2, and repeat. So always reject no sets, and yes sets we always accept, since it must in here or here. So the QFA can solve this problem only with two states, but any classical one is at least 2 to the k plus 1 states. That the reference of this proof is in the other reference, but I will skip. So the relations, last page that we remember, we should good things to remember in this presentation is that QFA is the most elementary model of QA, and QFA has been fully proved that has larger power than its classical counterpart DFA. And language recognized by QFA are not regular language, and I did not explain, but it is not same as the language recognized by the probabilistic finite automata QFA. The quantum is different with something that, and there are some open problems about the properties of quantum languages, since there are not only this RTQFA, but other quantum automata is defined many and many. Yeah. And real quantum computers have a difference between the QFA and real quantum computer, since real quantum computer has an input state, initial state as mixed state, since we cannot correct the states precisely in real world, but we assumed in QFA it starts with a pure initial state. So that's all in the all of this presentation, and this is the main reference of this presentation. This is main reference, and this reference said that he taught from the automata things in this book, and this recent research status, and this is some experimental tries about the QFA. So are there any questions?
Oh, thank you for your speech. I want to ask about which property of quantum automata or quantum dynamics makes QFA more powerful than DFA?
That is the probabilistic part, I think. Since the language recognition process is different with GFA and QFA. We define the in GFA. We can say the word is accepted or not with the final state, and the final state is determined anyway. The final state is determined as one of in the queue, but in cafe start the initial state was in queue, but the final state may not in queue. So with the language the language that QFA accepts we use the cut point lambda. We have had to take the lambda. So this, I think this is the point that separate the GFA and QFA. Okay. And another question.
You said QFA is more powerful than classical DFA for these examples.
Yes.
Is there any examples or case or task that classical automata is more powerful than QFA?
Yes, this problem, I think, in general case, QFA, there are I think the unitary operate, we can define the unitary operation well, then it would be equivalent with DFA, I think, but I don't know exactly. Sorry about that. Yeah. Other questions? Are there no questions? Then I'll finish this presentation. Thank you for listening.
Thank you for the presentation. And let's take a minute break.